Look up at the night sky, just for a moment. Each of those tiny, twinkling points of light is a sun, and around many of them are entire families of worlds we are only just beginning to understand. For all of human history, that profound question, "Are we alone?" has echoed in the silence of the cosmos, a mystery woven into our very existence. But right now, in our lifetime, that silence is finally being broken. We are living through a revolution in discovery, an era where the answer to that ancient question is shifting from the realm of philosophy into the tangible, data-driven world of science. We are no longer just wondering, we are actively hunting, and what we are finding is rewriting our place in the universe. It starts with a simple yet breathtakingly powerful idea, that among the countless stars, there must be other Earths, other worlds with the right conditions for life to spark and flourish. This isn't science fiction anymore. This is our new reality. Over the last few decades, a fleet of robotic explorers, eyes like the Kepler Space Telescope and TSS, have stared unblinkingly into the deep, cataloging a treasure trove of distant planets. They have revealed a galaxy that is far more crowded, diverse, and wondrous than we ever dared to dream. And nestled within this vast cosmic census are the crown jewels, exoplanets that sit perfectly within what astronomers call the habitable zone. Think of it as a star's Goldilocks zone, not too hot, not too cold, but just right for liquid water to potentially pool on a world's surface. Water is the universal solvent, the essential ingredient for life as we know it, and finding it is our first and most crucial clue. But the story doesn't end with temperature. The true nature of these worlds is a complex tapestry of atmosphere, composition, and stellar activity, a puzzle we are only just learning to solve. Today, we are going on a journey to 25 of the most promising, most fascinating planets scientists have identified as potential abodes for life. We will visit super-Earths with crushing gravity, water worlds shrouded in global oceans, and tidally locked planets where one side is in perpetual daylight and the other in endless night. Each one is a unique experiment in planetary science, a testament to the sheer variety of what is possible out there. So, get ready to leave our solar system far behind. We are about to tour the most Earth-like, alien landscapes ever discovered, and explore the compelling evidence that suggests we may not be alone in this great, dark ocean of stars after all. Our journey begins not in some distant, unreachable corner of the galaxy, but practically on our doorstep. Just over 4 light-years away, a cosmic stone's throw in the grand scheme of things, orbits a world that has captured the imagination of astronomers and dreamers alike, Proxima Centauri b. This is the closest known exoplanet to our solar system, a rocky world similar in size to our own, and it lives in the habitable zone of Proxima Centauri, the small, faint red dwarf that is our Sun's nearest stellar neighbor. The very idea is stunning, a potentially Earth-like world right next door, but the reality of this planet is a complex and dramatic story of extremes. Because it orbits so close to its dim star to stay warm, a full year on Proxima Centauri b passes in just 11 Earth days, and this intimate dance has a profound consequence. The planet is tidally locked. Much like our moon is to Earth, one hemisphere of this world is permanently bathed in the fiery, reddish glow of its sun, while the other is plunged into the frozen, unending blackness of space. This creates a planet of 2 starkly different realms. The day side could be scorching, while the night side might be cold enough to freeze an atmosphere solid. The most likely place for temperate conditions, and for liquid water, would be in the thin, ribbon-like border between these 2 extremes, a perpetual twilight zone where a strange and fragile ecosystem might cling to existence. And then there is the star itself. Proxima Centauri is not the stable, benevolent sun we know. It is a tempestuous red dwarf prone to violent outbursts. The planet is routinely lashed by stellar flares. Eruptions of radiation so powerful they can be hundreds of times more intense than anything our sun produces. These flares would not only batter the surface with deadly ultraviolet and X-rays, but could also systematically strip away the planet's atmosphere over billions of years, eroding any chance for a stable climate or a protective shield. So, is Proxima Centauri B a barren, irradiated rock, or could it be a haven? The possibility for life hinges on these brutal conditions. If the planet has a strong magnetic field like Earth's, it might deflect the worst of the stellar winds. If it has a thick, carbon dioxide-rich atmosphere, it could efficiently distribute heat from the day side to the night side, moderating the temperature extremes and creating a more global environment. There is even a chance that primitive life could exist in subsurface oceans, shielded from the radiation by a thick crust of ice. Proxima Centauri b presents us with our first, most immediate test case, a world that is simultaneously the most accessible and one of the most challenging for life we can imagine. It forces us to ask, just how tenacious can life be when faced with a universe of extremes? This dramatic tidal locking creates a truly alien geography, a planet divided into three distinct kingdoms of climate. On the permanent day side, you would find a searing desert, a landscape under the constant, unblinking stare of a swollen, crimson sun. Any water here would likely have boiled away eons ago, leaving behind a baked and barren crust. In stark contrast, the far side of the planet is a realm of eternal frost, a deep freeze so absolute that the very air could snow out onto the surface, creating a global glacier in the darkness. But between these two inhospitable extremes lies a narrow, ribbon-like region of profound possibility, the Terminator line. Imagine standing on this world, where the horizon curves upwards into a perpetual sunrise or sunset. One side of the sky is a dull, eternal red, while the other is a canopy of unyielding stars. This twilight band could be the only place on the entire planet where surface temperatures are stable enough for liquid water to exist, a thin, fragile oasis wrapped around the globe. Life, if it exists here, would be confined to this marginal strip, a constant traveler in the twilight, never venturing too far into the heat or the cold. But the surface might not be the only refuge. Scientists are intensely focused on another, even more compelling possibility: vast, global subsurface oceans sealed beneath a thick, protective crust of ice. This model suggests that Proxima b could be a water world, its entire surface frozen solid into a shell of ice dozens of miles thick, but with a liquid ocean lurking deep below, heated not by the distant sun, but by the internal warmth of the planet itself and the gravitational tug of war from its star. In such an environment, life would be completely isolated from the violent stellar flares raging above, thriving in the dark, abyssal waters around geothermal vents, much like the exotic ecosystems we find at the bottom of Earth's oceans. The potential for this kind of hidden biosphere brings us to the planet's greatest unknown, its magnetic field. This invisible shield is our planet's primary defense against the solar wind, a constant stream of charged particles flowing from the sun. For Proxima b, a strong magnetic field would be absolutely critical, a planetary umbrella deflecting the relentless, atmosphere-stripping blasts from its tempestuous star. Without it, the planet would have been stripped bare, its air and water slowly boiled away into the void of space over billions of years. The presence or absence of this magnetic shield is the central question in the ongoing debate about this world's true nature. Is Proxima Centauri b a scorched and airless rock, a cosmic cautionary tale about the fury of red dwarf stars? Or is it a resilient world, an armored fortress with a hidden, liquid heart, protecting a second genesis of life just next door? Our current telescopes cannot yet give us a definitive answer, but the next generation of observatories, like the James Webb Space Telescope and the enormous, extremely large telescope being built in Chile, are designed to probe the atmospheres of worlds like this. They will search for the chemical fingerprints of water vapor, carbon dioxide, and even signs of biological activity. The story of Proxima b is a perfect microcosm of our entire search for life, a reminder that a world in the habitable zone is not necessarily a habitable world, and that life, if it is out there, may be far more ingenious and tenacious than we can possibly conceive. Moving from our closest stellar neighbor, we venture just a bit farther, about 40 light-years away, to a planetary system that redefines the word neighborhood. Welcome to the TRAPPIST-1 system, a cosmic marvel that feels less like a star with planets and more like a compact, carefully arranged solar family. At its heart is a tiny, ultra-cool dwarf star, so faint and cool that it burns for trillions of years, outliving our own sun by an almost incomprehensible margin. Encircling this smoldering ember are not one or two, but 7 known rocky worlds, all packed into a region of space smaller than the orbit of Mercury around our sun. The scale is truly mind-bending. If you were standing on one of these worlds, the other planets would appear in your sky not as distant points of light, but as prominent, beautiful orbs, some appearing larger than our own moon. You could watch your neighboring worlds cross the sky, their surfaces clearly visible, creating a celestial ballet of unparalleled intimacy. And of this magnificent 7, one world in particular has captured the focused attention of astrobiologists, TRAPPIST-1e. This planet is a jewel. It's almost a perfect Earth twin in terms of its size and density, which strongly suggests a rocky composition familiar to our own. But its most enticing quality is its location, parked perfectly in the center of the star's habitable zone. It receives a similar amount of stellar energy from its small sun as Earth does from ours, making the possibility of a temperate, Earth-like climate a very real and thrilling prospect. This positioning makes TRAPPIST-1e arguably the most Earth-like exoplanet we have ever found in terms of its fundamental physical characteristics and its potential for moderate surface conditions. Yet, as with Proxima b, this system presents its own set of fascinating puzzles and possibilities. All 7 planets are almost certainly tidally locked to their star, meaning they have a permanent day side and night side. However, the presence of a potentially thick atmosphere could work to distribute heat around the globe, preventing the kind of extreme temperature divides we might expect. The atmosphere is the great unknown, the key that will unlock the true nature of this world. Is it a thick, Venus-like shroud of carbon dioxide, creating a runaway greenhouse effect? Is it a thin, Mars-like wisp, offering little protection? Or is it a balanced, nitrogen-rich atmosphere with the right pressure for liquid water to flow and pool on the surface? The staggering implication of the TRAPPIST-1 system is the potential for peer worlds. With 3 other planets, D, F, and G, also residing within the habitable zone's optimistic boundaries, we are presented with the incredible, almost science-fictional scenario of multiple habitable worlds orbiting the same star. Imagine the possibilities. If life did arise on one world, could it be transported to the others on fragments of rock blasted into space by asteroid impacts, seeding life throughout the entire system in a process called panspermia? We could be looking at a single, interconnected biological province, a stellar system teeming with life in a variety of forms, all sharing a common origin. This compact architecture makes the TRAPPIST-1 system a veritable playground for the next generation of telescopes. Studying the atmospheres of these worlds, one after the other, and comparing their chemical compositions will be like conducting a controlled experiment in planetary evolution. Why does one world have water while another is dry? What caused the climates on these sibling worlds to diverge? The answers we find here could teach us fundamental lessons about what makes a planet habitable and how common life-bearing worlds might truly be across the cosmos. TRAPPIST-1e is more than just a promising candidate. It is a symbol of cosmic fertility, a powerful hint that where conditions are right, planets can form in abundance, and life may find not just one, but many footholds. The incredible compactness of the TRAPPIST-1 system creates a celestial dynamic unlike anything in our own solar experience. The gravitational interplay between these 7 tightly packed worlds is a constant, gentle dance. Their close proximities mean they exert measurable tugs on one another, subtly influencing each other's orbits. This isn't a chaotic, destabilizing force. Instead, it's a finely tuned gravitational resonance. The planet's orbital periods are locked in a precise, repeating rhythm, like a complex piece of cosmic music. For instance, for every 2 orbits Planet B completes, Planet C completes 3. This gravitational harmony is likely what has kept the system stable over billions of years, preventing the planets from crashing into one another. This stability is a fundamental requirement for life to have any chance to arise and evolve. It suggests a system with a long, quiet history, a peaceful stellar neighborhood where environmental conditions could potentially remain constant for eons. But what would it actually be like to stand on the surface of TRAPPIST-1e? The view would be nothing short of breathtaking, a vista that would make our single moon seem lonely by comparison. Several of its sibling worlds would dominate the sky, appearing not as faint stars, but as vast textured disks, some larger than our full moon. You could watch the intricate orbital dance unfold in real time, seeing the phases of these other worlds change dramatically over just a few days. One might appear as a brilliant crescent, while another shows a fully illuminated face. The star itself, hanging overhead, would be a deep, salmon-colored orb about 3 times the size of our Sun in the sky. Yet it would provide only about the same amount of warmth and light as our Sun gives to Earth. This creates a profoundly different sense of place, a world that feels deeply connected to its celestial family, a single member of a visible, tangible community of planets. The most pressing question for this world, and indeed for all the TRAPPIST planets, is the presence of water. Being in the habitable zone means the energy from the star is right, but it doesn't guarantee that the planet has any water to be liquid. Scientists have developed 2 primary theories. One possibility is that these are true water worlds, their surfaces completely engulfed by a single, global ocean hundreds of miles deep. In this scenario, TRAPPIST-1e would be a planet with no continents, no mountains breaking the surface, just an endless, serene ocean under a pink sky. The other possibility is that these worlds are more like our own, a mixture of land and sea, with exposed continents and deep ocean basins. The initial density measurements from telescopes hint that the inner planets, including TRAPPIST-1e, are likely denser and rockier, possibly with less water, while the outer worlds seem lighter, suggesting they could be true ocean planets. This variation itself is a scientific gold mine, offering a chance to study how water is distributed across a single planetary system. The key to unlocking these mysteries rests on our ability to analyze their atmospheres, and that is precisely the mission of the James Webb Space Telescope. JWST is uniquely equipped for this task. Its powerful infrared eye can detect the minute dimming of starlight as a planet passes in front of its sun. During this transit, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific colors of this light. By analyzing the resulting spectrum, the chemical fingerprint of the atmosphere, scientists can determine its composition. For TRAPPIST-1e, they will be searching for the telltale signs of a life-friendly world. The detection of significant water vapor would be a monumental discovery. Finding carbon dioxide would suggest a working carbon cycle, and the holy grail would be the detection of gases like ozone or methane that, in certain combinations, could be potential biosignatures, hints of biological processes. The beauty of studying the TRAPPIST-1 system is that we can do this for not just one, but for multiple worlds in the habitable zone. We can compare the atmosphere of the potentially drier TRAPPIST-1e with that of the potentially water-rich TRAPPIST-1f. Why does one world have a thick atmosphere while another has none? What processes led to such different outcomes? The answers will provide a revolutionary new understanding of planetary evolution and the true requirements for a world to become a living one. The hunt for other Earths took a giant leap forward in 2014, with a discovery that felt like a page torn from a science fiction novel. For the first time, we had confirmed visual evidence of a world almost exactly our own size, tucked neatly into the warm embrace of its star's habitable zone. That world is Kepler 186f, and its discovery changed everything. Before this moment, many of the planets we had found in the Goldilocks zone were so-called super-Earths, worlds significantly larger and more massive than our own, where the conditions and even the geology could be wildly different. But Kepler 186f was a different class of find altogether. It told us that planets like ours, with a familiar scale and potential for a familiar surface, were not just theoretical possibilities, they were out there, waiting to be found. This planet orbits a red dwarf star, a class of star that makes up the vast majority of stars in our galaxy. The star, Kepler 186, is smaller and cooler than our Sun, which means its habitable zone is much closer in. A full year on this world passes in just 130 Earth days, but the most compelling fact is its size. It's only about 10% larger than Earth in radius. This small difference is absolutely critical. When a planet is that close to Earth's dimensions, the odds shift dramatically in favor of it being a rocky world, with a solid surface you could theoretically stand on, rather than a gaseous mini Neptune with no definable ground. It has the right foundation. The discovery was made by the Kepler Space Telescope, which used the transit method, staring at a patch of sky and waiting for the telltale, repetitive dimming of a star's light as a planet passed in front of it. Finding a signal as faint as that from an Earth-sized planet around a dim star was like trying to detect the shadow of a mosquito flying in front of a distant car headlight. The success of this detection proved that our technology and methods were finally powerful enough to find the smallest and most Earth-like worlds, opening a floodgate that would lead to thousands more such discoveries. Kepler 186f stands as a monument in the history of astronomy, the first tangible proof that planets with the basic ingredients for life are not one in a million rarities, but could be common features throughout the cosmos. It set the stage for every small, rocky world we have found since, transforming our search from a hopeful quest into a confident census of potentially living worlds. While the discovery of planets around red dwarf stars opened our eyes to the sheer abundance of worlds, the hunt was always for something that felt a little more like home, a world not just in the habitable zone, but one orbiting a star that looked like our own Sun. That monumental discovery arrived in 2015, heralding a planet that instantly captured the public imagination and earned a powerful nickname, Earth's cousin. Its official name is Kepler 452b, and it represents a profound shift in our understanding of where life could potentially thrive. This isn't just another planet. It's a glimpse into a parallel reality, a version of our own world in a different solar system. Kepler 452b orbits a star, Kepler 452, that is strikingly similar to our Sun. It belongs to the same G-type spectral class. It's only about 20% brighter, and it's nearly the same temperature. Even more astonishing, this star is 6 billion years old, about 1.5 billion years older than our own Sun. This means the Kepler 452 system has had an extra 1.5 billion years for life to develop, evolve, and potentially become complex, all under the steady, familiar light of a Sun-like star. The planet itself completes one orbit every 385 days, a year just 20 days longer than our own. The symbolism is powerful and immediate. Here is a world with an Earth-like year, circling a Sun-like star, residing perfectly within that star's habitable zone. The sheer number of parallels is what makes this discovery so compelling and so resonant. It suggests that the cosmic recipe that created our own living world is not a solitary fluke, but a formula that the universe has followed elsewhere. The planet is classified as a super-Earth, with a radius about 60% larger than our own planet. This size difference is significant, but not so vast that it necessarily precludes a familiar environment. A world of this scale could have a number of different identities. It might be a rocky planet, much like a larger version of Earth, with towering mountain ranges and deep, vast oceans. The increased surface gravity, perhaps around twice what we experience, would create a landscape with potentially flatter terrain, as mountains would be pulled down more forcefully, and any life forms would be stockier and more robust to handle the constant, heavier pull. Alternatively, it could be what scientists call a mini-Neptune, a world with a small, rocky core enveloped by a tremendously thick, deep atmosphere of hydrogen and helium. In this scenario, there would be no solid surface to walk on, only an endless, crushing, gaseous abyss that transitions into a supercritical fluid ocean deep below. The key unknown that separates these two starkly different fates is the planet's mass. Without knowing the mass, we cannot calculate its density, and without density, we cannot know if it is a solid world or a gaseous one. This remains one of the most critical unanswered questions about Kepler 452b. Yet, the possibility that it is a rocky super-Earth opens up breathtaking possibilities for its climate and geology. A larger rocky planet would likely have more internal heat from radioactive decay, which could power a more vigorous system of plate tectonics. Plate tectonics is a crucial engine for life on Earth. It recycles carbon, regulates our climate over long timescales, and helps build the diverse geology of continents and ocean basins. On Kepler 452b, this process could have been active for billions of years longer than on Earth, potentially creating a world of extraordinary stability and environmental richness. Its older sun, meanwhile, has been gradually increasing in brightness as it ages, a process our own sun will undergo in the distant future. This means the habitable zone has been slowly migrating outward over the eons. A billion years ago, Kepler 452b might have been cooler, a snowball world. Today, it could be experiencing a lush, tropical greenhouse climate, and in the far future, it might face a runaway greenhouse effect, turning into a scorching Venus-like hellscape. This presents a fascinating astrobiological window. If life did arise there, it has had an enormous head start. Imagine ecosystems that have evolved for an extra 1.5 billion years. What levels of complexity and intelligence could have emerged in that almost unimaginable span of time? The planet stands as a silent, ancient testament to the potential longevity of life in the cosmos, a world that has watched its star age and change, and may have adapted in ways we can only dream of. Kepler 452b is more than just a target in the search for life. It is a glimpse into Earth's own deep future, a reminder that our world is a moment in a much longer, cosmic story. While many of the worlds we encounter spark our imagination with possibilities, the next planet on our list stands out for a different reason. It presents astronomers with a rare and precious opportunity for definitive answers. Let's turn our attention to LHS 1140b, a super-Earth that is less of a mysterious speck and more of a perfectly positioned laboratory for the next phase of exoplanet science. Orbiting a quiet red dwarf star about 49 light-years away, this world is a heavyweight in the most literal sense. It's over 6 times the mass of Earth, but only about 1.7 times its size. This combination tells us something profound about its composition. It is incredibly dense, one of the densest exoplanets we've ever measured. That high density points to a world that is overwhelmingly rocky and metallic, likely featuring a massive, solid iron core that makes up a far greater proportion of the planet than Earth's own core does. Think of it not as a larger version of our own world, but as a planetary cannonball, a compact, solid sphere of rock and iron. This dense, metallic heart is more than just a geological curiosity. It could be the key to the planet's entire habitability. A large, molten iron core churning with heat could generate a powerful magnetic field, a planetary force field that would be absolutely essential for deflecting the charged particles and radiation streaming from its host star. Without such a shield, any atmosphere would be slowly but surely eroded away into the void, leaving the surface barren and exposed. LHS 1140b's star, fortunately, is one of the calmer red dwarfs we know, lacking the violent flare activity that plagues Proxima Centauri. This combination of factors, a quiet star, a likely strong magnetic field, and a dense, rocky body, makes this world one of the most stable and promising environments for life we have found around a red dwarf. But the single most exciting feature of LHS 1140b is its orientation. From our vantage point on Earth, this planet passes directly in front of its star, an event known as a transit. This is the astronomical equivalent of a perfect alignment, a cosmic gift that allows our telescopes to perform their most delicate work. During a transit, a tiny fraction of the star's light filters through the planet's atmosphere, if it has one. By analyzing that filtered light, breaking it down into its constituent colors to create a spectrum, scientists can identify the chemical fingerprints of the gases present. We are no longer just guessing about its conditions, we are on the verge of knowing. The James Webb Space Telescope has already set its sights on this world, and the data it collects could tell us if LHS 1140b possesses an atmosphere rich in nitrogen and oxygen, or if it is swaddled in a thick blanket of carbon dioxide. We might even detect the shimmering signature of water vapor, suggesting vast oceans on its surface. Adding another layer of profound intrigue to this world is its age. The LHS 1140 system is ancient, estimated to be around 5 billion years old. That makes it roughly 1 billion years older than our own solar system. This planet has existed in a stable, habitable zone orbit for 5 billion years. To put that in perspective, life on Earth needed only about 1 billion years to go from the first primitive single-celled organisms to the dawn of complex life. This world has had 5 times that long for the intricate dance of chemistry and evolution to potentially take hold. If life ever found a footing here, it has had an almost unimaginable head start, an eon of uninterrupted time to evolve, adapt, and perhaps even achieve complexity that dwarfs our own. Is LHS 1140b a rugged, shielded world with deep oceans and a stable climate, a testament to life's tenacity over cosmic timescales? Or is it a dense, airless sphere, a beautiful but barren monument to what might have been? The answers are no longer a matter of speculation but of imminent discovery, making this distant world one of the most critically important targets in our entire search for life beyond Earth. As we continue our tour of the most promising worlds, we encounter a planetary system that feels almost designed for life, nestled around one of the quietest and most ancient stars in our celestial neighborhood. Welcome to Teegarden Star, a faint, ultra-cool red dwarf located a mere 12 light-years away. This star is so dim that it wasn't even discovered until the year 2003, hiding in plain sight despite its proximity. Its 2 known planets, Teegarden Star B and C, are a remarkable pair, but it's Planet B that truly captivates scientists. With an Earth Similarity Index ranking among the highest ever calculated, this super-Earth is not just in the habitable zone. It is positioned so perfectly within that temperate band that some climate models suggest its surface could be genuinely Earth-like, with regions where liquid water could flow and pool without boiling away or freezing solid. What makes this world so compelling isn't just its location, but the serene character of its sun. Unlike the flare-prone violence of Proxima Centauri, Teegarden Star is a picture of stellar tranquility. It is an incredibly old and stable star, burning so slowly and calmly that it may be twice the age of our own solar system. This offers a profound advantage for the development of life, time, Imagine a world that has enjoyed a stable, gentle energy source for 8, 10, or even 12 billion years. That is an almost unimaginable span for biological processes to begin, to experiment, and to evolve toward complexity, all without the constant threat of stellar tantrums stripping away its atmosphere. A single year on this world, one full orbit, is a whirlwind by our standards, taking only about 4.9 Earth days. This incredibly short orbital period is a direct result of the planet huddling close to its faint, cool star to stay warm. Such a tight orbit would typically suggest tidal locking, yet some sophisticated climate simulations present a tantalizing alternative. It's possible that Teegarden star B has a rotation period that is not locked, but instead rotates in a so-called spin-orbit resonance, similar to Mercury in our own solar system. This could create a day-night cycle, distributing stellar energy more evenly across the globe, and preventing the extreme temperature divides of a permanent dayside and nightside. A planet with a rotating climate, a stable star, and a perfect position in the habitable zone becomes one of the most enticing candidates for a truly Earth-like environment we have yet discovered. The presence of a sibling planet, Teegarden star C, further enriches the story. Planet C orbits just outside the conservative habitable zone, in a region more akin to Mars, but the existence of two rocky worlds in the same system immediately raises the possibility of planetary science we can compare and contrast. If both planets formed with similar initial ingredients, why did one end up warmer and the other colder? Studying this sibling pair could reveal fundamental truths about how planetary climates are shaped over billions of years. The primary challenge in studying Teegarden star B is the same as with many red dwarf planets. Direct atmospheric detection is incredibly difficult because the star is so faint. However, its proximity to Earth and its perfect alignment for the radial velocity method, the technique used to discover it by measuring the star's subtle wobble, makes it a prime target for future technological marvels. The next generation of giant ground-based telescopes, with mirrors over 30 meters across, will have the light-gathering power to potentially analyze the thin atmospheric signature of this world. The dream is to one day detect the biosignature gases of a living biosphere on a planet that has known nothing but peace and stability for twice the age of our own Earth. But what if the most promising world for life isn't a rocky planet like Earth at all, but something entirely different, a new class of world we are only just beginning to understand? This brings us to one of the most thrilling and controversial discoveries in recent memory, K2-18b. This enigmatic planet defies easy categorization, blurring the lines between a super-Earth and a mini-Neptune. It's significantly larger and more massive than our world, suggesting a composition unlike anything in our solar system. For years, planets of this size were often dismissed as gas-shrouded spheres with no solid surface, making them poor candidates for life as we know it. But that all changed with a revolutionary concept, the Hycean world. Imagine a planet with a massive, globe-spanning ocean, not dozens of miles deep, but hundreds. This is not an ocean of water resting on a rocky seabed like on Earth, but a vast liquid water layer that transitions seamlessly into a supercritical fluid as immense pressures build with depth. This entire aquatic realm is enveloped by a thick, hydrogen-rich atmosphere, a shroud that could create a powerful greenhouse effect, trapping just enough heat from its red dwarf star to keep the global ocean liquid, even though the planet orbits much closer than Mercury does to our Sun. The very idea transforms our search for life, suggesting that habitable conditions could exist on worlds that are fundamentally alien in their architecture. The excitement around K2-18b exploded when the James Webb Space Telescope turned its gaze toward this distant world. By analyzing the starlight filtering through the planet's atmosphere during a transit, JWST's incredible sensitivity detected the clear chemical fingerprints of carbon-bearing molecules. The data revealed water vapor, confirming the presence of a substantial water reservoir. It also detected carbon dioxide and methane, two gases that on Earth are intricately linked with biological cycles. But the most electrifying and cautious finding was a potential hint of dimethyl sulfide, or DMS. On our planet, dimethyl sulfide is a sulfur compound produced almost exclusively by living organisms, specifically by phytoplankton in our oceans. There are no known non-biological processes on Earth that can generate DMS in significant quantities. Its detection in the atmosphere of a Hycean world would be, quite simply, the most compelling potential biosignature we have ever found. This single data point has propelled K2-18b to the forefront of astrobiology, but scientists are rightly approaching it with a blend of profound excitement and rigorous skepticism. The detection is still at the threshold of the telescope's capabilities, and the signal needs to be confirmed with further observations. The critical question is whether there could be an unknown abiotic, geological, or photochemical process on a hydrogen-rich world that could also produce dimethyl sulfide. The environment of a Hycean planet is so different from Earth that we must be exceptionally careful not to jump to conclusions. The next steps involve JWST staring at K2-18b for many more transits, gathering more photons to either solidify the signal or see it fade into statistical noise. If it holds up, the implications are staggering. We would have our first credible evidence of biological activity on another world, not on a terrestrial twin, but on a shrouded water world teeming with potential life in its dark, pressurized depths. The life we might find there would almost certainly not be familiar. In the sunlit upper layers of its ocean, where starlight can penetrate, photosynthetic organisms could potentially thrive. But deeper down, in the eternal darkness, life would have to rely on chemical energy, much like the organisms around hydrothermal vents on Earth's ocean floor. The possibility of a literally global biosphere, with life existing throughout the entire water column of a planet, opens up a new frontier in our imagination of what living worlds can be. K2-18b represents a fundamental pivot in the search for life, teaching us that we must look beyond Earth clones and be prepared for the truly unexpected. The universe, it seems, may have more than one way to cook up a habitable planet, and the path to discovering our cosmic neighbors might lead us to a strange, water-logged world under a pink sky. Now, let's shift our gaze to a world discovered by one of the most productive planet hunters of our time, the TESS mission. Meet GJ357d, a super-Earth that perfectly illustrates how a planet on the cooler, outer edge of the habitable zone might still become a paradise, all thanks to the power of a blanket. Orbiting a quiet M-type dwarf star about 31 light-years away, this planet is substantial, weighing in at roughly 6 times the mass of Earth. A year here lasts just under 56 Earth days, placing it in a region where, without an atmosphere, the surface would likely be a frozen wasteland. But that single word, if, changes everything. If GJ357d has managed to hold onto a dense, substantial atmosphere, something remarkable could happen. That atmosphere would act like a massive, planetary-scale greenhouse, trapping the faint heat from its cool star and redistributing it around the globe. This is the same basic principle that keeps our own planet warm, but on a super-Earth, the effect could be even more pronounced. A thick shroud of gases like carbon dioxide or methane could raise surface temperatures by dozens of degrees, potentially pushing them above the freezing point of water and creating pockets of stability where liquid water could persist. This transforms a world that might otherwise be an ice ball into a candidate for a temperate, and perhaps even comfortable, environment. The star it orbits adds another layer of promise. It's classified as a quiet red dwarf, meaning it lacks the violent flare activity that threatens to strip the atmospheres from planets like Proxima Centauri, b. This tranquility gives GJ357d a much better chance of holding onto that all-important atmospheric blanket over billions of years. The combination of its position and a calm star makes this system a particularly compelling target for future study. What's truly groundbreaking about this discovery, however, is what it said about the TESS mission itself. While Kepler looked at a single, distant patch of sky, TESS was designed to scan almost the entire heavens, focusing on the closest and brightest stars to Earth. Finding a potentially habitable world like GJ 357d so early in its mission was a resounding declaration of success. It proved that our solar neighborhood is rich with these kinds of worlds, and that we now have the tools to systematically map them out. GJ 357d isn't just a solitary candidate. It's a beacon, representing the first of many such discoveries from TESS, and a sign that potentially habitable worlds are likely common around the calm, small stars that dominate our galactic neighborhood. Continuing our exploration of TESS's remarkable discoveries, we arrive at a world that stands as a quiet triumph in the search for Earth-like planets, TOI 700d. While many of the planets we've discussed are larger super-Earths, this one is special because of its modest, familiar scale. It is an almost perfect Earth-sized world, a rocky sphere with a radius just over 1% larger than our own planet, and it resides with elegant precision in the habitable zone of its calm red dwarf star, located about 100 light-years away. The discovery of TOI 700d was a masterclass in patience and precision from the TESS telescope. The signal of this small world transiting its star is incredibly faint, a whisper of a dip in starlight that required multiple confirmations to verify it was real. Its identification proved that we can now reliably detect planets that are not just massive giants, but true Earth analogs in size, even around the dimmest and most common stars in our galaxy. But what truly sets this system apart is the stellar character of its sun, TOI 700. This red dwarf is a portrait of serenity. In a cosmic neighborhood often defined by stellar tantrums, this star is remarkably quiet, showing no signs of the violent flares that bombard planets like Proxima b with sterilizing radiation. This tranquility is the system's greatest gift. It provides a stable, gentle environment where an atmosphere, if one exists, could persist for billions of years without being stripped away, giving life the one thing it needs most: time. With a stable star and a perfect orbital position, the stage is set for a potentially habitable world. But the question of what kind of world it is leads us into a fascinating exercise in planetary modeling. Without direct atmospheric data yet, scientists have used advanced climate simulations to explore the range of possibilities for TOI 700d's surface, and they have painted several breathtakingly different portraits. One compelling scenario suggests it could be a water world, its entire surface enveloped by a single global ocean. In this version, TOI 700d would have no continents, no mountains breaking the surface, just an endless, serene sea under a deep red sun. The ocean depths could be abyssal, with water pressures building to incredible extremes, potentially hiding entirely unique ecosystems in the permanent dark. A second, equally plausible model imagines a world that looks strikingly like a younger Earth. This version of TOI 700d would have significant land masses with exposed continents and deep ocean basins, all shrouded under a thick, protective layer of clouds. These clouds would play a critical role in regulating the climate, reflecting just enough stellar energy back into space to prevent a runaway greenhouse effect, while simultaneously trapping sufficient heat to keep the surface warm. The presence of land would open the door for a much wider variety of environments, from vast coastal regions to inland deserts and forests, creating niches where life could diversify in complex ways. Adding another layer of wonder to this system is the presence of its planetary sibling. TOI 700d is the outermost of three known planets, with a smaller, inner world and a middle planet that is also a mini Neptune. This configuration gives us a miniature, comparative solar system to study. We can ask why one world ended up as a likely gaseous mini-Neptune, while another became a rocky, Earth-sized planet in the habitable zone. The answers to such questions help us understand the fundamental processes of planet formation and the distribution of materials that make one world a gas ball and another a potential cradle for life. The next great step for TOI 700D is, of course, atmospheric characterization. The James Webb Space Telescope has already begun this work, searching for the chemical fingerprints of water vapor, carbon dioxide, methane, and other gases that would tell us which of these climate models, if any, is correct. Finding evidence of a thick water vapor atmosphere would strongly support the ocean world hypothesis. Detecting a more balanced atmosphere with signs of oxygen and nitrogen would point toward a world with both land and sea. TOI 700D represents the new vanguard in exoplanet science. It's no longer just about finding a planet in the right place, but about systematically unraveling its true nature, moving from a point of light on a graph to a world with a defined climate, geography, and perhaps one day, the signature of a living biosphere. Sometimes, the most profound discoveries are not made in the glare of new data, but by looking more carefully at what we've already seen. This is exactly what happened with Kepler 1649c, a world that emerged from the archives as a stunningly close match to our own. After the Kepler Space Telescope ended its primary mission, a team of scientists and citizen scientists embarked on a meticulous review of its old data, double-checking the algorithms that had flagged potential planets. During this painstaking process, they found a signal that had been previously misclassified as a false positive, a tiny, repeating dimming of a distant red dwarf's light. This was no error, it was a planet, and not just any planet, but one of the most Earth-like worlds ever identified in terms of its fundamental physical properties. The numbers are what truly take your breath away. Kepler 1649c is a mere 6% larger than Earth in diameter, a difference so minor that the odds are overwhelmingly in favor of it being a rocky world with a solid surface. Even more crucially, calculations show it receives about 75% of the stellar energy that Earth gets from the Sun. To put that in perspective, if you took our world and moved it just a bit farther from the Sun, that's roughly the amount of warmth it would experience. This places it firmly and comfortably within the conservative habitable zone, a region where a planet with an Earth-like atmosphere could easily maintain liquid water on its surface without it boiling away or freezing solid. It's not on the extreme, frigid outer edge or the scorching inner boundary. It's right in that sweet spot. This combination of an almost perfect Earth size and an Earth-like energy budget makes Kepler 1649c one of the most compelling analogues to our own planet we have ever found, a world that feels less like a distant possibility and more like a cosmic cousin. The intrigue of this system doesn't stop with this one remarkable world. Kepler 1649c orbits its star every 19.5 Earth days, and it is not alone. Another planet, a rocky body roughly the size of Venus, orbits much closer to the star in a blisteringly fast 3.4-day year. This inner world is almost certainly a scorched, hellish landscape, likely mirroring the conditions on Venus in our own solar system. This configuration is deeply suggestive. We have a Venus-like world close to the star, and an Earth-like world farther out in the temperate zone. This is a direct, if smaller scale, parallel to the architecture of our own inner solar system. While we have found many multi-planet systems, few so clearly echo the specific structure of our own cosmic neighborhood, with one potentially habitable world and one inferno. This pattern hints that the processes that shaped our solar system, with rocky planets forming at different distances from their sun, leading to dramatically different climates, might be a common outcome of planetary formation throughout the galaxy. It suggests that for every star like ours, there could be systems with their own versions of Venus and Earth, each on their own unique evolutionary path. Of course, the familiar caveats of red dwarf systems still apply. The planet is almost certainly tidally locked to its star, presenting the now familiar dichotomy of a permanent day side and night side. The stability of its climate and the potential for liquid water would therefore depend heavily on the presence and composition of an atmosphere. A thick atmosphere could work to distribute heat efficiently, preventing the day side from becoming a furnace and the night side from becoming an ice trap. Furthermore, the star itself is an active red dwarf, prone to flares. The planet's long-term habitability would hinge on whether it possesses a protective magnetic field to shield its atmosphere from being eroded by these stellar outbursts over billions of years. Yet, despite these challenges, Kepler 1649c stands as a powerful symbol of hope and potential. Its discovery in reanalyzed data is a thrilling reminder that our celestial treasure maps may still hold undiscovered gems, and that a world that looks and feels remarkably like our own could be waiting in the records, just needing a fresh pair of eyes to be found. Now, let's journey to a system where the sky itself is a work of art. A place not with one sun, but three. Our next destination is the remarkable GJ 667 system, where we find not one, but two super-Earths orbiting within the habitable zone of their primary star. The star they circle, GJ 667c, is a small red dwarf that is itself part of a complex triple-star family, sharing its cosmic neighborhood with two other orange dwarf stars that dance together in a wide orbital embrace. From the surface of either planet, the primary sun would be a dominant feature, but the two companion stars would also be visible, appearing in the sky not as faint dots, but as intensely brilliant stars, shining with the collective light of many full moons and casting faint, multiple shadows across the landscape. This creates a celestial environment unlike any we know, a permanent trinary twilight that bathes these worlds in an ethereal, multi-directional light. The most famous of these worlds is GJ 667cc, a planet that caused a sensation when it was discovered. It is a super-Earth with a mass about 3.5 times that of our own planet, and it orbits its dim red sun in a mere 28 days. The truly stunning fact is that despite this incredibly short year, the planet receives almost exactly the same amount of light energy from its star as Earth does from the Sun. This perfect positioning, right in the heart of the star's habitable zone, combined with its likely rocky composition, initially made GJ 667cc one of the highest-ranked habitable planet candidates, a world that seemed to have all the basic ingredients for a temperate climate. Yet, the presence of its stellar siblings adds a layer of profound complexity to this seemingly idyllic picture. While the two other stars are far enough away that they don't drastically heat the planet, their gravitational influence is a constant, subtle force on the entire system. The potential for gravitational tugs and long-term orbital perturbations is a real factor that could affect the climate stability of these worlds over millions of years. A planet's climate depends on a stable orbit. If that orbit is constantly being gently nudged and reshaped by the pull of other stars, it could lead to chaotic climate shifts, swinging between ice ages and hothouse periods in a geologic heartbeat, making it difficult for life to gain a steady foothold. This introduces a critical concept in our search for life: the difference between being in the habitable zone and being truly habitable. GJ 667cc has the right amount of energy, but the stability of its environment is an open question influenced by the complex gravitational dance of its triple-star home. The story of this system becomes even richer when we meet GJ 667c's sibling, the less famous but equally fascinating GJ 667cf. This planet orbits a little farther out from the star than CC, with a year lasting 39 days, placing it on the cooler, outer edge of the habitable zone. The discovery of two rocky worlds orbiting within the temperate zone of the same star is a monumental finding. It immediately doubles the chances for life in this single system, and presents us with a natural laboratory to study comparative planetology. We can ask why two worlds, formed from the same primordial disk of dust and gas around the same star, might have evolved such different climates and conditions. Perhaps GJ6, 167cc, the inner world, is a warmer, more tropical planet, while GJ667cf is a cooler world, potentially a snowball planet with ice-covered surfaces that only thaw around the warmer equatorial regions. Or, if both possess thick atmospheres, they could both enjoy global, temperate conditions, with CF relying more heavily on a greenhouse effect to stay warm. The very existence of this pair challenges our understanding and forces us to consider that habitable worlds may not be solitary outposts, but might often come in sibling pairs or even whole families, clustered around the small, long-lived stars that make up the majority of our galaxy. However, a shadow of uncertainty has been cast over these promising worlds in recent years. As astronomers have collected more data, some studies have suggested that the original signals of these planets might be fainter and more ambiguous than first thought. The subtle wobbles in the star that indicated their presence could potentially be confused with the star's own magnetic activity and sunspot cycles. This is not uncommon in the fraught and difficult science of exoplanet detection, especially around active red dwarfs. It highlights the rigorous, self-correcting nature of science, where initial excitement is always tempered by follow-up observations and deeper analysis. The current consensus is that GJ667cc very likely does exist, but its properties and even the existence of GJ667cf are subjects of ongoing investigation and debate. This uncertainty doesn't diminish their importance. Instead, it makes them a classic case study in the challenges of modern astronomy. They represent the frontier of discovery, where the line between a confirmed world and a data ghost is incredibly fine. The next generation of telescopes will be crucial for resolving this mystery, either by confirming their presence through direct imaging or by precisely measuring their gravitational influence to finally pin down their exact masses and orbits. The tale of the GJ667 system is a captivating blend of cosmic grandeur and scientific caution. It offers a vision of multiple habitable worlds under triple suns, a scene of breathtaking beauty, while simultaneously reminding us that every new discovery must be scrutinized and validated, a painstaking process that separates the mirages from the genuine oases in the vast desert of space. Now, let's travel over 1,000 light-years away to a system that feels like a glimpse into a parallel reality. A family of worlds that expanded our very definition of what a habitable zone could be. Discovered by the Kepler telescope, the Kepler 62 system is home to a pair of super-Earths that captured the world's attention, not for being Earth twins, but for being something entirely different and wondrous, a potential binary of living worlds. Orbiting a star cooler and older than our Sun, these two planets, Kepler 62e and Kepler 62f, are a study in contrasts, demonstrating the range of environments that can exist within a single star's temperate band. The inner world, Kepler 62e, is a larger super-Earth, orbiting its star in about 122 days. It sits on the warmer, inner edge of the habitable zone, a position that suggests a world with a powerful greenhouse effect. Imagine a planet perpetually shrouded in thick, water vapor clouds, with surface temperatures that could be consistently tropical. The most compelling models for this world painted as a true water world, a global ocean planet with no land in sight. Its entire surface would be a single, endless sea, likely thousands of miles deep, with conditions at the ocean floor so extreme that the water itself would be compressed into exotic forms of ice. Yet, in the sunlit upper layers of this vast aquatic realm where starlight can penetrate, the conditions could be surprisingly hospitable for life. This is a world defined by its water, a global aquatic environment on a scale that dwarfs our own planet's oceans. Its sibling, Kepler 62f, is the crown jewel of the system and a prime example of a world that is perfectly poised for habitability. It's slightly smaller and cooler, orbiting farther out in a 167-day year. This places it squarely in the conservative, safer region of the habitable zone, where the risk of a runaway greenhouse effect is much lower. With a radius only about 40% larger than Earth's, it is one of the most likely worlds we have found to be a rocky planet with a solid surface. The combination of its size and its position makes it one of the strongest candidates we have for a potentially life-bearing world. The prevailing hypothesis is that Kepler 62f is not just a water world, but the water world, an entire planet where the dominant feature is a global, liquid ocean. If it possesses an Earth-like atmosphere with sufficient nitrogen and carbon dioxide, its climate could be remarkably stable, with a global temperature that allows for a persistent liquid water surface. The presence of a magnetic field and active geology would be critical, as they would help recycle nutrients and maintain a stable climate over billions of years. The truly breathtaking implication of the Kepler 62 system is the potential for two different types of habitable environments orbiting the same star. One world could be a warm, tropical water planet, while the other is a cooler, perhaps even icy, ocean world. If life exists in this system, it could have arisen independently on each planet, or it could have been transported between them via asteroids, creating a single, interconnected biological province with life forms adapted to two distinct, but neighboring aquatic worlds. While Kepler 62f shows us the potential of water worlds, our next destination introduces a factor absolutely critical for the kind of complex, abundant life we see on Earth: the power of light. Meet Kepler 442b, a super-Earth orbiting a star substantially different from the red dwarfs we've frequently encountered. Its host is a K-type star, often called an orange dwarf. These stars are a perfect middle ground. They are warmer, larger, and more stable than the flaring red dwarfs, yet they are smaller and longer-lived than our own G-type Sun. This stellar stability offers a huge advantage for the long-term evolution of life, providing a calm, predictable energy source for billions of years. But the truly revolutionary aspect of Kepler 442b is something scientists call photosynthetically active radiation. In simple terms, this planet receives from its star a quality and quantity of light that is almost identical to what Earth receives from the Sun. Think about that for a moment. The sunlight that fuels nearly every ecosystem on our planet, that drives the growth of forests and phytoplankton blooms, could be shining down on the surface of this distant world. This isn't just about temperature. It's about energy availability for the most fundamental biological process we know. For a planet to develop a complex, oxygen-rich biosphere like Earth's, it needs a primary producer, an organism that can capture stellar energy and convert it into chemical fuel. On our world, that's photosynthesis. Kepler 442b is the first exoplanet where we can confidently say the light from its star is sufficient to power photosynthesis. This doesn't mean there are forests there, but it means the foundational energy source required for a complex, multi-layered food web is present. This single fact elevates it from being merely a potentially habitable world to being a planet that could, in theory, support a biosphere of a complexity and richness that we would recognize. It suggests that if life found a foothold there, it would have the fuel to evolve beyond simple microbes into larger, more complex organisms, all under the gentle, orange-tinged light of a stable and long-lived sun. While many of the worlds we've explored feel distant, our next discovery brings the search for life remarkably close to home. A mere 14 light-years away, practically a stone's throw in cosmic terms, orbits a super-Earth named Wolf 1061c. This world holds the distinction of being one of the very closest potentially habitable exoplanets we know of, making its entire system an irresistible target for our most powerful telescopes. It orbits a stable red dwarf star, a star that is both older and calmer than our own Sun, offering a potentially peaceful environment for billions of years. But the true nature of this nearby world is a story of delicate balance, a planetary high-wire act between two dramatically different fates. Wolf 1061c resides at the inner edge, the warmer boundary of its star's habitable zone. This positioning is both its greatest promise and its most significant peril. It exists in a climatic sweet spot that is incredibly narrow. On one hand, with the right atmospheric composition, it could be a perfectly temperate world, perhaps even warmer than Earth, with large tropical regions and open oceans. On the other hand, if its atmosphere is too thick with greenhouse gases like carbon dioxide or water vapor, it could have succumbed to a runaway greenhouse effect. This is the same cataclysmic process that scientists believe transformed Venus from a world that might have once had oceans into the scorching, acid-laced hellscape it is today. The runaway effect begins when a planet absorbs more heat from its star than it can radiate back into space. This causes surface temperatures to rise, which in turn evaporates more water into the atmosphere. Since water vapor is itself a potent greenhouse gas, this creates a vicious, self-reinforcing cycle. The temperature climbs higher and higher, eventually boiling the oceans away entirely and baking the planet's surface under a crushing, toxic shroud. So, the central question for Wolf 1061c is a matter of atmospheric fine-tuning. Did it form with just enough of an atmosphere to create a comfortable greenhouse blanket, or did it tip over the edge into a Venus-like inferno? The planet's mass, over 4 times that of Earth, suggests it has a strong gravitational pull, which would help it hold onto a substantial atmosphere. But what is that atmosphere made of? Is it a nitrogen-oxygen mix like our own, a dense carbon dioxide cloak like Venus, or something else entirely? Its location in a multi-planet system offers another fascinating clue. Wolf 1061c is the middle child of 3 known planets. Its inner sibling, Planet B, orbits too close to the star to be anything other than a molten wasteland, while its outer sibling, Planet D, sits at the habitable zone's cooler outer frontier, a world that might require a strong greenhouse effect just to avoid freezing over. This family portrait gives us a perfect comparative laboratory. By studying all 3 worlds together, we can begin to understand how the same initial ingredients, circling the same star, can lead to such vastly different outcomes based solely on their distance from their sun. The incredible proximity of this system is what truly sets it apart. 14 light-years is an almost trivial distance on the galactic scale. This makes Wolf 1061c one of the very first planets that future missions, like proposed space-based direct imaging telescopes, could actually attempt to photograph. Instead of just inferring its existence from a wobble or a dimming of starlight, we might one day see it as a tiny, pale blue, or perhaps pale orange, dot next to its reddish sun. Such a direct image would allow us to analyze its light in extraordinary detail, searching for the reflections of continents and oceans, and perhaps even detecting the spectral signature of chlorophyll or other pigments that would be a near certain sign of a living biosphere. Wolf 1061c stands as a constant, nearby reminder of the fine line worlds walk between paradise and purgatory, a world whose secrets are tantalizingly within our future reach. But a planet's potential isn't just about its star. It's also about the company it keeps. For our next world, we find ourselves in a system that feels bustling and dynamic, a far cry from the solitary worlds we often imagine. Welcome to HD 40307G, a super-Earth that offers a different kind of promise, one born from the gravitational complexity of a multi-planet family. Orbiting a K-type orange dwarf star about 42 light-years away, this planet stands out because it is not a lone child. It is one of at least 6 known worlds all circling the same sun. This creates a celestial environment rich with gravitational interactions, a constant, gentle push and pull that could have played a crucial role in shaping the planet's very capacity for life. The star itself is a significant upgrade in stability compared to the flaring red dwarfs we've visited. K-type stars are calmer and longer-lived than even our own Sun, offering a steady, benevolent light for tens of billions of years. This extended timeline provides an almost unimaginable window for the slow, patient dance of chemistry and evolution to unfold. A year on HD 40,307 G lasts about 200 Earth days, placing it comfortably within the star's habitable zone. But its most defining characteristic is its sheer physical presence. This is a substantial world with a mass at least 7 times greater than Earth's. That immense bulk translates directly to a powerful surface gravity, likely more than twice what we experience here. Walking on this planet would feel like carrying another entire person on your shoulders at all times. This intense gravity would sculpt the world in profound ways. The landscape would likely be far flatter and smoother than Earth's, with any mountain ranges pulled down under their own weight, unable to reach the towering heights of our Himalayas. The atmosphere would be denser and pressed closer to the surface, and any oceans would be deep, with waves that are slower and more ponderous. This heavy world presents a fascinating paradox for habitability. On one hand, the strong gravity makes it an excellent atmosphere trap. It would be incredibly difficult for any atmospheric gases to escape into space, meaning HD 40,307 G could have held onto a thick, protective blanket of air over billions of years. This same gravity, however, poses unique challenges. Volcanic activity, which on Earth helps recycle carbon and regulate our climate, might be suppressed, as the planet's massive weight could prevent the tectonic plates from moving as freely. The pressure at the bottom of any ocean would be crushing, potentially creating a layer of exotic high-pressure ice at the seafloor, separating the liquid water above from the rocky mantle below, and limiting the exchange of minerals that life often depends on. Yet, the very fact that it exists within a crowded system of planets is a point in its favor. Multi-planet systems are often gravitationally stable over the long term, and the complex orbital resonances between the worlds can help shepherd asteroids and comets, potentially delivering the water and organic compounds that are the building blocks of life early in the system's history. HD 40,307 G is a world of grand scales and powerful forces, a planet where life would have to adapt to a heavier, denser existence, but one that has enjoyed the steady, unwavering light of a reliable sun for eons, a stability that makes it a prime candidate for a complex and enduring biosphere. Now, let's turn our attention to a quiet but profoundly promising world found in the vast ocean of data from the Kepler mission, Kepler 1229b. This super-Earth serves as a perfect reminder that sometimes the most compelling candidates for life aren't the ones making the loudest headlines, but those that simply present an enduring, stable environment where biology could quietly take root and thrive. Nestled in the habitable zone of its red dwarf star, this planet stands out for one particularly compelling metric: its Earth Similarity Index. This index is a tool used by astronomers to quantify how closely an exoplanet's physical conditions match those of our own world, taking into account factors like size, density, and the amount of energy it receives from its star. Kepler 1229b scores remarkably high on this scale, indicating that it possesses a foundational recipe that is strikingly familiar. It's a world that isn't just in the right place. It has the right basic building blocks. Orbiting its star in a leisurely 86-day year, this planet is positioned with elegant precision in the very center of the star's temperate band. This central location is a significant advantage. Unlike worlds perched on the inner or outer edges of the habitable zone, where climates can swing toward runaway greenhouse effects or global ice ages, a planet in the middle enjoys a more moderate and stable energy balance. It's a position that allows for a wider range of atmospheric conditions to still result in a temperate surface, giving life a more forgiving environment in which to emerge. The planet's size strongly suggests a rocky composition, a terrestrial world with a solid surface that could feature familiar landscapes of mountains, valleys, and, most importantly, basins where liquid water could collect. This combination of an Earth-like size and a perfect orbital position makes Kepler 1229b one of the most convincing hypothetical Earth analogues we have discovered. A world that feels less like a bizarre alien landscape and more like a potential second home. But the true gift of this system lies in the character of its sun. The host star is a red dwarf, but it belongs to a much calmer and more mature class than the violent, flare-prone stars we've encountered elsewhere. It is relatively inactive, meaning it lacks the frequent, violent outbursts of ultraviolet and X-ray radiation that can systematically strip away a planet's atmosphere and bathe its surface in sterilizing radiation. This stellar tranquility cannot be overstated in its importance for long-term habitability. While a planet might start with all the right ingredients: water, a rocky surface, a thick atmosphere, a hostile star can ruin everything. Here, the quiet nature of the star offers a protective cocoon, a stable energy source that has likely remained consistent for billions of years. This provides the one ingredient life needs most above all else: time. On Earth, it took roughly 1 billion years for the first primitive life forms to appear. A world like Kepler 1229b, orbiting a placid star, has been granted the profound gift of eons, a multi-billion-year stretch of stability for the slow, intricate dance of prebiotic chemistry to potentially cross the threshold into biology, and for that life to then evolve in complexity without being periodically reset by stellar tantrums. The prospect of a stable climate over such cosmic timescales opens the door to a world that may have developed its own rich and complex story. A narrative written not in years, but in geological eras, all unfolding under the gentle, crimson light of a quiet sun. But as our catalog of worlds grows, we begin to notice a curious pattern. The most common potentially habitable planets seem to orbit small, red dwarf stars. This makes sense statistically, as these stars are the most abundant in the galaxy. Yet it raises a fundamental question: is our own situation, a rocky world orbiting a stable, sun-like star, a cosmic rarity? The discovery of Kepler 1638b offers a powerful and reassuring counterpoint to that idea. Here we have a super-Earth, a world about 60% larger than our own, orbiting a star that is strikingly similar to our Sun in both its class and its temperature. This is a much less common find, and it makes this world profoundly significant. It's not just another candidate, it's a glimpse into a parallel evolutionary path, a what-if scenario unfolding around a star that could be our Sun's distant twin. The very nature of its sun changes the entire habitability equation. Unlike a red dwarf whose habitable zone is so close that planets become tidally locked and battered by flares, a sun-like star offers a more generous and temperate region. Kepler 1638b orbits at a much more comfortable distance, with a year lasting over 250 Earth days. This distance alone reduces the risk of tidal locking, meaning this world could very well have a regular day-night cycle, spinning on its axis just as Earth does, with the star rising and setting in a familiar rhythm that drives weather patterns and allows for a more even distribution of heat across the entire globe. The star's stability is another key advantage. Sun-like stars are far less prone to the violent, atmosphere-stripping superflares that are common in youthful red dwarf systems. This provides a much calmer and more predictable environment over billions of years. A steady, unwavering light under which life would have the quiet consistency it needs to not only emerge, but to complexify without constant environmental upheaval. The planet's size, while larger than Earth, places it in that intriguing super-Earth category, which opens up a fascinating range of possibilities for its actual environment. A world of this scale likely has a stronger gravitational pull, which would help it retain a substantial atmosphere, a crucial shield against cosmic radiation, and a blanket to maintain surface warmth. This stronger gravity would also profoundly shape its topography. Mountain ranges might be pulled lower and wider, and any continents could be flatter, with coastlines leading to deep, vast ocean basins. The planet's increased mass would also suggest a more vigorous and long-lasting internal heat engine, potentially powering a robust system of plate tectonics. This geological recycling process is on Earth, a critical planetary thermostat. It helps regulate the amount of carbon dioxide in the atmosphere over million-year timescales, preventing the climate from spiraling into either a permanent icehouse or a runaway greenhouse. If Kepler 1638b has active tectonics, it would be a powerful indicator of a world capable of maintaining environmental stability across geological epochs. The presence of a molten core could also generate a global magnetic field, deflecting the stellar wind and providing an additional layer of protection for any developing atmosphere. So, what might the surface of such a world actually be like? With its stable star and strong potential for a thick atmosphere, it could enjoy a climate not too dissimilar from Earth's, albeit on a grander scale. Imagine a landscape with weather systems of immense power and scope, with storms that span entire continents and jet streams that race around the planet. Its larger surface area means there is simply more room for environments to diversify, more space for vast, shallow seas, sprawling continental shelves, and immense inland deserts. It could be a world of superlatives, with biodiversity thriving across a wider range of ecological niches than our own planet possesses. The discovery of Kepler 1638b is a critical piece of evidence in the grand puzzle of cosmic life. It tells us that while habitable worlds around red dwarfs may be common, the conditions that forged our own Earth, a rocky planet with a day-night cycle, orbiting a steady, sun-like star, are also being replicated out there in the cosmos. It reassures us that our own solar system is not a bizarre outlier, but one version of a story that the universe is telling again and again. This world is a benchmark, a point of comparison that allows us to calibrate our understanding of what makes a planet not just habitable, but truly Earth-like in its most fundamental stellar context. While many red dwarf stars are tempestuous and unpredictable, our next destination offers a glimpse into a far more serene and stable cosmic neighborhood. Just 11 light-years away, a stone's throw in interstellar terms, orbits Ross 128b, a world that presents one of the most compelling and balanced cases for potential habitability we have yet encountered. What makes this planet so special isn't necessarily its own physical properties, though they are promising, but the remarkably tranquil character of the star it calls home. Ross 128 is a red dwarf, but it stands apart as one of the quietest stellar citizens in our entire galactic vicinity. Unlike the flare-prone violence of Proxima Centauri or the youthful agitation of many other small stars, Ross 128 is a portrait of stellar maturity and calm. It exhibits extremely low flare activity, meaning it doesn't routinely blast its planetary family with the deadly ultraviolet and X-ray radiation that can strip away atmospheres and sterilize surfaces. This stellar tranquility is the system's greatest gift. For a planet to sustain life over billions of years, it needs a stable environment, and a quiet star provides the consistent, gentle energy required for chemistry to become biology, and for that biology to evolve in peace. It means that any atmosphere Ross 128b managed to acquire during its formation could have been preserved, creating a protective shield that has endured for eons. The planet itself is an Earth-sized world, a rocky body with a mass about 1.3 times that of our own planet. This modest size is a crucial detail. It strongly suggests a terrestrial composition with a solid surface, rather than a gaseous mini-Neptune. A year on this world is incredibly short by our standards, a whirlwind 11-day orbit around its dim sun. This close proximity is necessary to stay within the star's warmth, but it places Ross 128b at the inner edge, the warmer boundary of the habitable zone. It receives about 38% more stellar radiation than Earth does from the Sun. At first glance, that might sound like a recipe for a runaway greenhouse effect, a Venus-like fate where the oceans boil away. However, the potential for a temperate climate here hinges on a delicate and fascinating atmospheric balancing act. The key lies in the planet's ability to reflect a significant amount of that incoming energy back into space, a property scientists call albedo. If Ross 128b has a substantial atmosphere with a healthy layer of clouds, or if its surface is covered in bright, reflective ice or sand, it could effectively bounce enough of that extra heat away to maintain a comfortable surface temperature. The presence of an atmosphere is what transforms this world from a scorched rock into a potential oasis. A blanket of air, perhaps rich in nitrogen with moderate amounts of carbon dioxide, could distribute heat from the permanent day side to the night side, moderating the extreme temperature differences that would otherwise exist on a tidally locked world. The result could be a planet where the most habitable region is a wide, temperate band in the eternal twilight of the Terminator line, or perhaps even a globe with a largely temperate climate, if the atmosphere is thick enough to facilitate efficient heat transfer. This combination of factors, a quiet star, an Earth-like size, and an orbit that is potentially warm but not definitively scorching, makes Ross 128b a prime target for the next generation of astronomical study. Its proximity to Earth is a tremendous advantage, making it one of the closest potentially habitable exoplanets known. This relative nearness means that its signal is stronger, and it is a brighter target for our most powerful telescopes. The ultimate goal is to use instruments like the James Webb Space Telescope to perform a spectroscopic analysis of its atmosphere. By observing the starlight that filters through the planet's air as it transits its star, we could search for the chemical fingerprints of water vapor, carbon dioxide, methane, and even oxygen. Finding a combination of these gases, particularly in the presence of that all-important cloud cover, would strongly suggest a world that has managed to maintain a stable, liquid water climate despite receiving a bit more sunlight than our own planet. Ross 128b stands as a testament to the idea that habitability is not a single set of conditions, but a spectrum. It challenges the simple Goldilocks narrative and shows us that a world can be slightly warmer, slightly closer to its star, and still be a viable home for life, so long as it has the right atmospheric conditions and, most importantly, a calm and stable sun to watch over it. It represents a different path to potential life, one defined not by perfect Earth-like parallels, but by planetary resilience and stellar peace. Now, let's turn our attention to a fascinating stellar family located just over 20 light-years away, the HD2 19134 system, a bustling cosmic neighborhood that showcases the stunning diversity of worlds that can form together. Here, we encounter two very different planets, both with intriguing claims to habitability, but for entirely different reasons. This pair, HD2 19134G and HD2 19134H, offer a perfect side-by-side comparison of two distinct pathways a world might take. Planet G is a classic super-Earth, a dense, rocky world with several times the mass of our own planet, and it orbits near the warmer, inner boundary of its star's habitable zone. This positioning suggests a world that could be quite warm, perhaps even tropical, if it possesses an atmosphere capable of regulating its climate. Its sibling, Planet H, is a different beast entirely. It's a mini Neptune, a world significantly larger and less dense, likely composed of a rocky core surrounded by a deep, massive envelope of hydrogen and helium gas. Planet H orbits farther out in the system, in a cooler region, yet it still resides within the star's extended habitable zone. The existence of these two worlds in the same system forces us to expand our definition of what a habitable planet can be. We are so accustomed to searching for rocky twins of Earth that we can overlook the possibility that life might find a way in environments that are completely alien to our own experience. A rocky super-Earth like Planet G represents the familiar path, a world where life could potentially arise on a solid surface, in oceans and on continents, much like our own planet. But the mini-Neptune, Planet H, represents a frontier of astrobiological possibility that is only just beginning to be explored. Let's explore the potential of the rocky world first. HD 2-19134G, with its substantial mass and likely solid surface, presents a scenario we can more easily envision. Located near the inner edge of the habitable zone, its fate is a delicate balancing act. With a thick atmosphere rich in reflective clouds, it could potentially moderate the intense stellar energy it receives, leading to a stable, warm climate with vast, shallow seas. However, if its atmosphere is too thick with greenhouse gases like carbon dioxide, it could have succumbed to a runaway greenhouse effect, transforming it into a scorching hellscape similar to Venus. The presence of other planets in this crowded system adds another layer of complexity. The gravitational interactions between these worlds could have influenced Planet G's early history, potentially affecting how much water and other volatile compounds it was able to acquire and retain. If it has managed to hold onto its water and maintain a stable climate, it could be a world of dramatic weather and powerful storms, with a geology shaped by its stronger gravity, leading to flatter mountain ranges and deeper ocean trenches than we see on Earth. The possibility of an active interior, driving plate tectonics and a protective magnetic field, would further enhance its credentials as a prime candidate for a living world. Now, let's venture into the truly alien environment of the mini-Neptune, Planet H. This world has no solid surface as we know it. Instead, imagine descending through layers of a vast, perpetually cloudy atmosphere that grows steadily thicker and hotter with depth, eventually transitioning into a supercritical fluid ocean above a core of rock and ice. For decades, such a world would have been written off as completely uninhabitable. But recent research has revealed a startling possibility. A habitable band could exist high in the atmosphere of a mini-Neptune. At a specific altitude, the atmospheric pressure and temperature might be just right for liquid water droplets to form and persist. In this strange, suspended oasis, free-floating microbial life could potentially exist, buoyed by atmospheric currents and using the faint starlight filtering through the haze for energy. These would not be creatures that walk or swim, but aerial organisms, drifting through the skies of a gas giant in a perpetual, global aerial plankton. The concept challenges our very definition of a biosphere, suggesting that life doesn't necessarily need a planetary surface. It just needs a stable environment with the right chemistry and an energy source. And the potential for life in this system doesn't end with the planet itself. A massive world like HD 2-19134H, with its strong gravity, is a prime candidate for hosting a system of large, robust moons. Much like the moons of Jupiter in our own solar system, but on a larger scale, these exomoons could be rocky, Earth-sized worlds themselves, orbiting within the protective magnetic field of their giant parent. Tidal forces from the planet could provide immense internal heat, powering volcanic activity and maintaining subsurface oceans of liquid water beneath icy crusts. An exomoon orbiting Planet H would have a dual energy source, warmth from the star above and even more potent heat from the tidal flexing induced by the planet below. Such a moon could be a fully fledged water world, its hidden ocean teeming with life, all while circling a gas giant that hangs majestically in its sky. The HD 2-19134 system, with its rocky super-Earth and its gaseous mini-Neptune, beautifully illustrates that the habitable zone is not a one-size-fits-all region reserved only for Earth clones. It is a broad arena where many different kinds of worlds can exist, each with its own unique set of possibilities for hosting life, whether on a familiar rocky surface, suspended in the clouds of a gas giant, or hidden beneath the ice of a captured moon. This cosmic diversity reminds us that life, if it is out there, may be far more adaptable and widespread than we have ever imagined. Yet another nearby star holds a world that perfectly embodies the delicate balance between hope and caution in our search for life. A mere 12 light-years from Earth, the star Tau Ceti has long been a beacon in our night sky and a fixture in our science fiction, often portrayed as the home of advanced civilizations. The reality is perhaps even more intriguing, centered on one of its known planets, Tau Ceti e. This super-Earth orbits a star that is a near twin to our Sun, a rare and precious G-type yellow dwarf, offering a stellar environment far more stable and familiar than the flaring red dwarfs that host so many other candidates. A year on this world is a brisk 168 Earth days, a rapid orbit that places it squarely on the warmer, inner edge of Tau Ceti's habitable zone. This pivotal location is what makes Tau Ceti e such a compelling puzzle, a world balanced on a knife's edge between two dramatically different fates. On one hand, its position suggests it could be what scientists term a super-Venus, a scorched and hostile world where a runaway greenhouse effect has boiled away any oceans and left the surface a molten wasteland under a crushing, toxic atmosphere. The intense stellar energy it receives could have triggered an irreversible cycle of heating, making it a cautionary tale of a planet that strayed too close to its sun. Yet, sophisticated climate models reveal another, more hopeful possibility. The true nature of a planet's surface is not dictated by starlight alone, but by the intricate interplay between that energy and the planetary atmosphere. If Tau Ceti e formed with an atmosphere that is thinner than Venus's, or one with a different composition, perhaps richer in nitrogen and with just the right amount of reflective cloud cover, it could have developed a powerful cooling mechanism. Such an atmosphere could bounce a significant portion of the incoming stellar radiation back into space, effectively creating a planetary sunshade. In this scenario, the surface temperature could be stabilized within a comfortable, temperate range, potentially allowing for liquid water and conditions that, while likely warmer than Earth's, could still be hospitable to life. The planet's size, estimated to be around 4 times the mass of Earth, adds another layer of complexity. This substantial bulk would generate a strong gravitational field, which would be excellent for holding onto a life-sustaining atmosphere over billions of years. However, that same powerful gravity would profoundly shape any potential biosphere. Walking on this world would feel immensely heavy, and the landscape would likely be far flatter, with any mountain ranges pulled down under their own weight. Oceans would be deeper and more pressurized, and any life that evolved would need to be sturdy and robust, built to withstand a constant, crushing force. The star Tau Ceti itself is a cosmic icon, not just for its similarity to our Sun, but for its role as one of the primary targets in the search for extraterrestrial intelligence, or SETI. For decades, radio telescopes have been pointed at this nearby sun, listening intently for any artificial signal, any whisper of technology that would announce we are not alone. While no such signal has ever been confirmed, the very fact that Tau Ceti is a priority for these searches underscores its profound significance. It represents the hope that a stable, sun-like star would be the most logical place for a civilization like our own to arise. The discovery of planets like Tau Ceti e only deepens this intrigue, providing a tangible, physical destination for that hope, a specific world around a familiar star that could, under the right conditions, harbor not just life, but perhaps intelligence. Ultimately, Tau Ceti e serves as a critical lesson in exoplanetary science. It teaches us that a planet's position in the habitable zone is a starting point, not a guarantee. Two worlds with identical orbits could have wildly different destinies based solely on the history of their atmosphere and geology. This super-Earth challenges us to look beyond simple labels and reminds us that the difference between a tropical paradise and a scorching hellscape may be as delicate as the composition of the air. Its mystery is one that future telescopes are poised to solve. By analyzing the light filtering through its atmosphere, and finally determining whether this nearby world is a cautionary tale or a stunning confirmation that life can flourish under suns very much like our own. The journey to map our cosmic neighborhood is rarely a simple one, and perhaps no other world exemplifies the thrilling, and at times contentious, nature of this search better than GJ 581G. Its story begins with a burst of excitement in 2010, when a team of astronomers announced they had found not just another exoplanet, but a landmark discovery. The first world beyond our solar system that was both rocky and resided squarely in the middle of its star's habitable zone. This wasn't a world on the extreme edges of possibility. Based on the data, it was a prime candidate, a super-Earth with the potential for a truly Earth-like climate. The news rippled through the scientific community and captivated the public, instantly becoming a symbol of a new era in the hunt for life. But the initial fanfare was soon met with a wave of skepticism, plunging GJ581G into a controversy that would last for years and teach us invaluable lessons about the painstaking difficulty of finding other Earths. To understand why this planet became so controversial, we need to explore the primary tool used to discover it, the radial velocity method. Imagine a star sitting in the void of space. It's not perfectly stationary. If it has planets, their gravity, however faint, tugs on the star, causing it to wobble in a tiny, delicate dance. This wobble is what astronomers measure. As the star moves slightly toward us, the light waves it emits are compressed, shifting them very slightly toward the blue end of the spectrum. As it moves away, the light waves are stretched, shifting them toward the red. By meticulously tracking these subtle red shifts and blue shifts in the star's light over months and years, scientists can infer the presence of unseen planets, calculate their mass, and determine the length of their year. It's an incredible technique, but it's also like trying to measure the wobble of a car's headlight from thousands of miles away caused by a mosquito landing on its hood. The signals are incredibly faint, buried within the inherent noise and activity of the star itself. For the red dwarf star GJ581, astronomers were trying to untangle the gravitational signatures of multiple planets from this delicate data, a task akin to isolating individual instruments in a complex symphony from a recording filled with static. The controversy around GJ581G erupted because different teams, looking at largely the same set of radial velocity data, came to dramatically different conclusions. The original discovery team, led by Stephen Vogt, applied a complex statistical analysis to the star's wobbles and concluded that the data could only be explained by the presence of a new planet, G, with a mass just over 3 times that of Earth and an orbital period of only 37 days. This placed it perfectly in the star's habitable zone. However, other research groups, when they reanalyzed the data, argued that the signal attributed to planet G was not a distinct planetary signature at all. They suggested it was an artifact, a false pattern created by the combined gravitational pulls of the other known planets in the system interacting with the star's own natural activity cycles. Stars like GJ581 have magnetic fields and starspots similar to sunspots that can cause their brightness and spectral lines to vary, creating a kind of stellar noise that can mimic or mask the subtle signal of a small, orbiting planet. The central debate boiled down to a fundamental question: were scientists seeing a true planetary wobble, or were they seeing the echo of the star's own heartbeat, misinterpreted through the lens of sophisticated mathematics? This intense disagreement was not merely an academic squabble. It was a necessary and healthy part of the scientific process. Extraordinary claims require extraordinary evidence, and the claim of finding the first truly Earth-like habitable world was certainly extraordinary. The scientific community responded by demanding more data and more independent verification. The controversy over GJ581G forced a crucial conversation about the standards of proof in exoplanet science, particularly for small, rocky worlds in the habitable zone where the signals are at the very limit of our detection capabilities. It highlighted the challenges of working with red dwarf stars, which are often magnetically active and prone to spots and flares that can confound radial velocity measurements. This period of doubt and reanalysis pushed the entire field to develop more robust data processing techniques and to be more cautious and transparent in its claims. For years, the status of GJ581G remained in a kind of scientific limbo, a promising world that might not exist. The initial excitement gave way to a more sober and meticulous phase of investigation. Then, in 2020, a major new study using a powerful and improved statistical model re-examined the entire GJ581 dataset, incorporating hundreds of new observations. This comprehensive analysis concluded that the evidence for a planet with the characteristics of GJ581G was, in fact, significant. The new model did a better job of separating the stellar activity from the genuine planetary signals, and it found that the wobble attributed to planet G was persistent and statistically robust. While not every scientist is fully convinced, the consensus has now shifted significantly back toward the planet's likely existence. This dramatic reversal offers a powerful testament to the self-correcting nature of science, where patience, improved technology, and relentless scrutiny ultimately help us move closer to the truth. The story of GJ581G is far more than a tale of one world's disputed discovery. It is a masterclass in the challenges of modern astronomy, showing us that the path to finding a new Earth is paved with careful measurement, healthy skepticism, and the slow, steady accumulation of knowledge that, in the end, brings our cosmic map into sharper focus. And so we reach the final stop on our tour of potentially habitable worlds, a planet that holds a special place in the history of exoplanet science. Let's turn our attention to Kepler 22b, a world whose name itself evokes the pioneering spirit of the mission that found it. When the Kepler Space Telescope launched, its primary goal was to answer a single, profound question: how common are Earth-sized planets in the habitable zones of stars like our Sun? For years, we had found gas giants and worlds in scorching orbits, but the true Earth analogs remained elusive. Then, in 2011, came the announcement that changed everything: the confirmation of Kepler 22b. This wasn't just another planet. It was the very first world discovered by Kepler to orbit squarely within the habitable zone of a Sun-like star. The psychological impact of that discovery cannot be overstated. It was the moment the hypothetical became real. We had long theorized that other stars must have their own temperate regions, but here was definitive proof that these cosmic Goldilocks zones were not barren. They were occupied. The star, Kepler 22, is a G-type star very similar to our own Sun, and the planet circles it in a 290-day year, an orbital period that feels hauntingly familiar. The data told us that this world received about 25% less light from its star than Earth gets from the Sun, suggesting a climate that might be a bit cooler overall, but still very much within the range where liquid water could exist. This confirmation was a validation of the entire Kepler mission and a beacon of hope, signaling that we were finally on the right track in our search for other Earths. The physical nature of Kepler 22b, however, is where the story becomes more complex and fascinating. With a radius measuring about 2.4 times that of Earth, this planet is firmly in the category of a super-Earth. But that size places it directly on the cusp of a critical planetary divide. Is it a massive, rocky planet with a solid surface, often called a mega-Earth? Or has its size tipped it over into the realm of the mini-Neptunes, a world with a small rocky core enveloped by a deep, immense atmosphere of hydrogen and helium. The majority of evidence and scientific modeling currently points toward the latter. A planet of this scale likely has too much bulk to be purely rocky. Its immense gravity would have allowed it to accrete and hold onto vast amounts of hydrogen and water during its formation in the early days of the planetary system. This leads to the prevailing theory that Kepler 22b is what scientists term a water world or a gas-enveloped planet. Imagine a landscape, or rather, a seascape, that is utterly alien to our own. There would be no continents, no mountain ranges breaking a rocky crust. Instead, the entire surface would be a single global ocean, hundreds or even thousands of miles deep. As you descend, the pressure would build to unimaginable levels, eventually compressing the water into exotic, hot forms of ice, like Ice 7. A crystalline form that remains solid at extremely high temperatures, creating a layer of solid water separating the liquid ocean above from the rocky silicate mantle far below. This water world hypothesis opens up a breathtaking, though challenging, possibility for life. The surface of such a global ocean could be perpetually shrouded in a thick water vapor haze, with temperatures potentially hovering around a comfortable, lukewarm level. In the sunlit upper layers where starlight can penetrate, a unique aquatic biosphere could thrive. Photosynthetic organisms, similar to algae or phytoplankton on Earth, could float in these vast, warm seas, forming the base of a food web that might support more complex life forms. Yet, the challenges are immense. Without land, the planet would lack the mineral nutrient cycles that are so crucial for life on Earth. The only source of new minerals would be from upwellings from the deep, or from the scant dust of asteroids and comets that manage to penetrate the atmosphere. Furthermore, the incredible depth and pressure of the ocean would create a world with no solid substrate, an environment where the very concept of a foothold is foreign. Life here would be forever adrift, an eternal planktonic existence in a world with no shores. The possibility also exists that the atmosphere is so thick with hydrogen that the surface pressure is crushing, creating a greenhouse effect so powerful that the water is actually superheated, making the surface environment more like a scalding pressure cooker than a tranquil sea. Kepler 22b, therefore, presents us with a paradigm of potential habitability that is entirely different from our own. It forces us to consider that a living world does not need to look like Earth. It could be a vast, dark, abyssal globe where biology has found a way to exist in a perpetual, planet-wide sea. The true, enduring legacy of Kepler 22b, however, transcends the ongoing debate about its surface conditions. Its greatest gift to humanity was one of profound perspective. Before its discovery, the habitable zone was a theoretical line on a chart, a calculated region where conditions might be right. Kepler 22b transformed that abstract circle into a tangible destination. It was the first piece of hard evidence that the universe actually builds planets and places them in these life-friendly orbits around stars like our own. This single data point gave weight to our statistical models and fueled the optimism that would lead to thousands more Kepler discoveries. It proved that the processes that formed our solar system were not unique. The telescope's method of discovery, waiting for the tiny, repetitive dimming of the star's light as the planet transited, was itself a triumph of engineering and patience. Confirming a planet like this required witnessing multiple transits, which meant waiting for it to complete several of its 290-day orbits. This was a multi-year investment of observation and analysis, a testament to the long-term commitment required to do this science. The public announcement in 2011 was a global event, capturing headlines and imaginations everywhere. It wasn't just a discovery for astronomers, it was a discovery for all of humanity, a shared moment of cosmic revelation. Kepler 22b became a symbol, a name that represented the turning of a page. It marked the end of an era of wondering and the beginning of an era of knowing. It taught us that to find new Earths, we must first be willing to find worlds that are profoundly alien, and to recognize that the path to answering our oldest question is paved with stepping stones that are each, in their own way, revolutionary. This incredible journey across 25 worlds, from our stellar doorstep to distant water planets, brings us to a pivotal crossroads in our quest. We have moved from simply asking, "Are there other planets?" to a far more profound and detailed inquiry, "Are any of these worlds actually alive?" The next great leap in this cosmic detective story is already underway, shifting our focus from discovery to characterization, from finding dots of light to unraveling the intricate details of alien climates and potential biospheres. The future of this search rests on the shoulders of a new generation of astronomical observatories, instruments so powerful they will transform these faint, distant specks into worlds with defined atmospheres, weather patterns, and just maybe, the chemical signatures of life. Leading this charge is a revolutionary concept known as the Habitable Worlds Observatory, or HWO. Imagine a space telescope with a mirror so large and precise, and a coronagraph so advanced that it can physically block out the blinding glare of a host star. This would allow it to directly see and photograph the faint, orbiting planets themselves. We are no longer talking about inferring a planet's existence from a wobble or a dimming of starlight. We are talking about capturing its actual pale blue dot, or perhaps pale green dot, floating in the blackness. This direct image would be a monumental achievement, but HWO's true power lies in what it can do with that light. It would break the planet's reflected light into a spectrum, a unique chemical barcode that reveals the precise composition of its atmosphere. This is how we will move from speculation to knowledge. The ultimate goal of this detailed atmospheric analysis is the search for biosignatures, combinations of gases that are difficult to explain without the presence of life. The most famous of these is oxygen. In Earth's atmosphere, oxygen is abundant and highly reactive. Without the continuous, planet-wide process of photosynthesis carried out by plants, algae, and cyanobacteria, it would quickly vanish, binding with rocks and oceans. Finding significant, persistent oxygen in the atmosphere of a rocky exoplanet, especially alongside a gas like methane which oxygen should rapidly destroy, would be a tremendously exciting signal. This dynamic disequilibrium, where two gases that should cancel each other out coexist, is a powerful, though not definitive, hint of a biosphere actively maintaining that balance. But scientists are wisely cautious. We must be absolutely certain we are not being fooled by geological or chemical processes we haven't yet imagined. A planet might build up oxygen through the photodissociation of water vapor, where intense stellar radiation breaks apart water molecules without any biology involved. This is why the context is everything. The discovery of a biosignature would not be a simple one-and-done announcement. It will be a gradual process of building evidence. The presence of oxygen alone is suggestive, but oxygen plus methane is more compelling. Add to that the detection of water vapor and global surface temperatures consistent with liquid water, and the case grows stronger. Then, imagine if we also detect a glint of light reflecting off a surface ocean, or seasonal changes in the planet's coloration that mimic the growth and decay of vegetation. The Habitable Worlds Observatory is designed to gather exactly this kind of multi-layered evidence, building a robust, contextual argument for life rather than relying on a single, ambiguous clue. Beyond HWO, an entire arsenal of new tools is coming online to deepen our investigation. The extremely large telescope, currently being built in the Chilean desert, will have a primary mirror nearly 40 meters across, making it the largest optical telescope in the world. Its immense light-gathering power will allow it to study the atmospheres of some of the closest exoplanets, like those in the Proxima Centauri and LHS 1140 systems, in extraordinary detail. Meanwhile, the James Webb Space Telescope continues its mission, using its unparalleled infrared sensitivity to probe the atmospheres of transiting planets like those in the TRAPPIST-1 system, searching for the molecular fingerprints of water, carbon dioxide, and other key compounds. These telescopes work in concert, each with its own strengths, creating a complementary network of cosmic observers. The search is also expanding beyond traditional biosignatures to include what are known as technosignatures. These are signs of advanced technology, such as narrowband radio transmissions, laser pulses, or even the artificial illumination of a planet's night side. While the detection of a technosignature remains a long shot, it represents the thrilling possibility that we might not just find life, but intelligence. The future hunt for habitable worlds is therefore a multi-pronged effort, combining the search for biological imprints with the search for technological ones, covering the entire spectrum of possibilities for what, or who, we might find out there. This next chapter is not just about building bigger telescopes. It is about developing more sophisticated ways of interpreting the data they send back, allowing us to peer across the light years and finally answer the question that has haunted humanity for millennia. From our very closest stellar neighbor, Proxima Centauri b, to the distant, ancient systems like Kepler 1649c, this journey has revealed a galaxy that is not just vast and empty, but positively teeming with potential. A galaxy where the basic ingredients for life, rocky worlds, stable orbits, and the delicate balance of temperature for liquid water appear to be common, almost mundane. These 25 worlds are far more than just entries in a scientific catalog. They are individual testaments to nature's boundless creativity in constructing planets. Each one, from the tidally locked red dwarf companions to the serene water worlds and bustling multi-planet systems, tells its own unique story of cosmic evolution, a story of how a swirling cloud of dust and gas can coalesce into a place that just might cradle life. We have transitioned from an era of wondering if such places exist to an era of detailed inquiry, of asking not if they are out there, but what they are truly like. We are now standing at the precipice of the next great age of discovery, an age defined not by finding new dots on a map, but by learning to read the stories those dots have to tell. The atmospheres of these distant worlds are the next frontier, and with the revolutionary power of telescopes like the James Webb Space Telescope and the future Habitable Worlds Observatory, we are on the cusp of analyzing their chemical compositions from across the light years. We will search for the subtle, telltale signatures of water vapor, the stark imbalance of oxygen and methane that hints at biological activity, and the reflective glint of sunlight on a vast, alien ocean. The question is no longer about possibility, but about presence. We are actively developing the tools to move from a list of promising addresses to a genuine understanding of which ones are truly living worlds. This search is one of the most profound endeavors humanity has ever undertaken. It touches on our deepest questions about our own origins and our place in the cosmos. To find life elsewhere, even in its most primitive microbial form, would be a discovery on par with the Copernican revolution, fundamentally reshaping our understanding of biology and our own significance in the universe. It would tell us that the universe is not just habitable, but inhabited, that life is a natural and common outcome of cosmic evolution. The silence of the cosmos, which has felt so immense and empty for so long, may finally be broken by the faint, chemical whisper of a biosphere on a world orbiting a distant star. So now, we turn the question over to you. After exploring these 25 incredible candidates, which one captures your imagination the most? Do you believe the most promising world is the serene, ancient tranquility of Teegarden's star B, a planet that may have enjoyed stability for twice the age of our Earth? Or does the familiar, sun-like star of Kepler 452b, a world with a billion-year head start on evolution, seem like the most likely place for a complex biosphere to have taken root? Perhaps you're drawn to the strange, aquatic mystery of K218b, a Hycean world where life might exist not on a surface, but suspended in a global ocean under a hydrogen sky. Let us know your thoughts and which world you would most want to see with your own eyes in the comments below. This conversation is just beginning, and every new observation brings us closer to an answer. If you want to continue exploring the greatest mysteries of the cosmos with us, be sure to subscribe and hit the notification bell so you don't miss our next journey into the unknown. The universe is